capacitor is an electronic component that stores electrical energy in an electric field. Capacitors perform several functions in electronic circuits. Firstly, energy storage. Capacitors store electrical energy when a voltage is applied across them. Secondly, filtering. Capacitors filter out unwanted frequencies in signals, allowing only desired frequencies to pass through. Thirdly, smoothing. Capacitors smooth out voltage fluctuations or ripples in circuits. Fourthly, timing. Capacitors can be used to set the time constants of circuits, controlling the rate of charging and discharging. Fifthly, blocking direct current. Capacitors can block direct current while allowing alternating current to pass through. A capacitor consists of two conductive plates separated by an insulating material called a dielectric. The plates store the electrical charge, while the dielectric prevents current flow between them. There are several types of capacitors. 1. Ceramic. These are small, inexpensive, and used in high-frequency applications. 2. Electrolytic. These are larger, polarized capacitors with high capacitance values. 3. Film. These are made of thin film materials, offering stability and low losses. 4. Supercapacitors. These can store large amounts of energy in a small volume. Capacitance is measured in farads. A capacitor with a capacitance of 1 farad can store 1 coulomb of electrical charge at a potential difference of 1 volt. Capacitors are widely used in electronic devices and systems, including power supplies, filtering circuits, timing circuits, energy storage devices, and electrical noise suppression. Let's delve deeper into the characteristics and applications of capacitors. The behavior of a capacitor in a circuit is governed by its capacitance, which is the measure of its ability to store electrical charge. A capacitor's capacitance is determined by several factors, including the area of the plates, the distance between the plates, and the dielectric material used. Increasing the area of the plates increases the capacitance, while increasing the distance between the plates decreases the capacitance. The dielectric material also plays a crucial role, as different materials have different dielectric constants, which affect the capacitance. When a voltage is applied across a capacitor, charge accumulates on the plates. One plate accumulates positive charge, while the other plate accumulates negative charge. The amount of charge stored is directly proportional to the voltage applied and the capacitance of the capacitor, as described by the equation Q equals C times V, where Q is the charge, C is the capacitance, and V is the voltage. The energy stored in a capacitor is given by the equation E equals 1/2 times C times V squared, where E is the energy, C is the capacitance, and V is the voltage. This equation highlights the fact that the energy stored in a capacitor increases with both capacitance and voltage. Capacitors exhibit different behaviors in direct current and alternating current circuits. In a direct current circuit, a capacitor initially acts as a short circuit, allowing current to flow freely as it charges up. However, once the capacitor is fully charged, it acts as an open circuit, blocking the flow of current. In an alternating current circuit, a capacitor continuously charges and discharges, allowing current to flow through the circuit. The opposition to current flow offered by a capacitor in an alternating current circuit is called capacitive reactance, which is inversely proportional to the frequency of the alternating current and the capacitance of the capacitor. Capacitors are used in a wide variety of applications, including power supplies, where they are used to filter out voltage ripples and provide a stable direct current voltage. They are also used in filtering circuits, where they are used to block unwanted frequencies or pass desired frequencies. In timing circuits, capacitors are used to control the rate of charging and discharging, which can be used to create time delays or generate specific waveforms. Capacitors are also used in energy storage devices, such as supercapacitors, which can store large amounts of energy in a small volume. Furthermore, capacitors are used in electrical noise suppression circuits, where they are used to reduce unwanted noise and interference. When selecting a capacitor for a particular application, it is important to consider several factors, including the capacitance value, voltage rating, temperature coefficient, and equivalent series resistance. The capacitance value should be chosen based on the specific requirements of the circuit. The voltage rating should be high enough to withstand the maximum voltage that will be applied across the capacitor. The temperature coefficient indicates how much the capacitance will change with temperature. The equivalent series resistance represents the internal resistance of the capacitor, which can affect its performance in high-frequency circuits. Understanding the different types of capacitors and their characteristics is essential for designing and troubleshooting electronic circuits. Ceramic capacitors are known for their small size, low cost, and high-frequency performance. Electrolytic capacitors are polarized, meaning they have a positive and negative terminal, and they offer high capacitance values, making them suitable for applications where large amounts of energy storage are required. Dome capacitors offer good stability and low losses, making them suitable for precision circuits. Supercapacitors offer very high capacitance values and can store large amounts of energy in a small volume, making them suitable for applications such as energy harvesting and backup power. In addition to the factors mentioned earlier, it is also important to consider the tolerance of a capacitor, which indicates the range of possible capacitance values for a given capacitor. A capacitor with a tight tolerance will have a capacitance value that is close to the specified value, while a capacitor with a wider tolerance may have a capacitance value that deviates more from the specified value. The choice of capacitor tolerance depends on the specific requirements of the circuit. In some applications, a tight tolerance is essential, while in other applications, a wider tolerance is acceptable. Another important consideration is the lifespan of a capacitor. Capacitors can degrade over time, especially when subjected to high temperatures or voltages. The lifespan of a capacitor is typically specified in terms of IOs at a certain temperature and voltage. When selecting a capacitor, it is important to choose one with a lifespan that is appropriate for the application. Capacitors are also used in power factor correction circuits. Power factor is a measure of how efficiently electrical power is used. A low power factor indicates that a significant portion of the electrical power is being wasted. Capacitors can be used to improve the power factor by providing reactive power, which cancels out the reactive power drawn by inductive loads such as motors and transformers. By improving the power factor, capacitors can reduce energy consumption and improve the efficiency of electrical systems. Capacitors also play a crucial role in resonance circuits. A resonance circuit consists of a capacitor and an inductor connected together. At a specific frequency, called the resonant frequency, the impedance of the capacitor and the inductor cancel each other out, resulting in a very high current flow. Resonance circuits are used in a wide variety of applications, including radio receivers, oscillators, and filters. The resonant frequency of a resonance circuit is determined by the capacitance of the capacitor and the inductance of the inductor. In addition to the applications mentioned earlier, capacitors are also used in sensors. Capacitive sensors measure changes in capacitance to detect changes in physical quantities such as pressure, temperature, and humidity. Capacitive sensors are used in a wide variety of applications, including automotive systems, industrial automation, and medical devices. The sensitivity of a capacitive sensor is determined by the geometry of the capacitor and the dielectric material used. Capacitors are also used in touchscreens. Touchscreens use a grid of capacitors to detect the location of a touch. When a finger touches the screen, it changes the capacitance of the capacitors in the grid. The touchscreen controller then detects these changes in capacitance and determines the location of the touch. Touchscreens are used in a wide variety of devices, including smartphones, tablets, and computers. The accuracy and resolution of a touchscreen are determined by the density of the capacitors in a grid. Furthermore, capacitors are used in medical devices, for instance, in defibrillators. Defibrillators use capacitors to store electrical energy, which is then delivered to the heart to restore a normal heart rhythm. The amount of energy stored in the capacitor is determined by the capacitance and the voltage. Defibrillators are used in emergency situations to save lives. It's also worth noting that capacitors are used in high-voltage power transmission systems. High-voltage power transmission systems use capacitors to improve the stability of the grid. The capacitance is used to reduce voltage fluctuations and prevent power outages. Capacitors are also used to improve the efficiency of the grid by reducing transmission losses. In summary, capacitors are fundamental electronic components with a wide range of applications. Understanding their characteristics, types, and applications is essential for anyone working with electronics. Whether you are designing circuits, troubleshooting equipment, or simply interested in learning more about electronics, a solid understanding of capacitors will serve you well. From energy storage to filtering, timing, and sensing, capacitors play a vital role in modern technology. As technology continues to advance, capacitors will continue to evolve and find new applications.